name's Martin, and I work for an organisation called the Bluetooth Special Interest Group. And most people have never heard of us, don't know who we are. Bluetooth is a standard, and we're the organisation behind that standard. So we're a standards body. That's the type of organisation that we are. We don't make anything. We don't make Bluetooth products. We don't make software. We don't make electronics. We're responsible for the engineering specification that defines how Bluetooth works. And then manufacturers implement to that spec, and we have some kind of quality assurance procedures they have to go through, and so on. And you may or may not know, Bluetooth's actually been around, I'm moving away from the mic now, rookie mistake. 20 years, it says it here, so it must be true. So that's quite a long time for any technology, really, because they tend to kind of come and go, and some of them never even arrive. We get all excited about this new thing that's going to be amazing, and then it fizzles out and doesn't quite happen. So Bluetooth's been around for a long time for a number of reasons, but one of them is that it hasn't stood still. It's evolved, it's changed, it's offered developers new capabilities, it's evolved to meet new use cases, and so on. And I'm here to talk about a new Bluetooth technology called Bluetooth Mesh, which definitely falls into that category. One number for you, I don't kind of like doing marketing statistics, but I quite like this one. In the year 2000, there were a total of 800,000 Bluetooth devices that were kind of released into the world. Now there are 10 million every single day. It's like, okay, that's a large number. It's like 4 billion every year. And it's showing no signs of kind of plateauing yet. So it's very ubiquitous. So for developers, it is quite an important communications technology to know about. So let's start. So we've actually got 3 Bluetooth technologies now. You may or may not be aware of this. So on the left there, we have Bluetooth BR EDR. That's basic rate, enhanced data rate, and that actually is the original Bluetooth, the one that came out 20 years ago. It's effectively a cable replacement technology, and it lets you form one-to-one kind of point-to-point connections between 2 devices as if they had a cable, but it's invisible. And it was designed really to handle cases where there's a steady stream of data. So it's very good at things like audio. If you've got wireless headphones, almost certainly that's what it uses. Okay, and it's the oldest of the Bluetooths, plural, is that right? I don't know, of the Bluetooth technologies, but it's still very strong. It's very strong in anything that involves audio. Bluetooth Low Energy in the middle there, it's been around for about 8 years now, and it had very different design goals, and technically it's very different to BR-EDR. Very power efficient. It was intended that devices should be able to communicate wirelessly using as little power as possible, so they could run from tiny batteries for many years. I've got some devices at home that have what I believe are the world's smallest solar panels, and they're powered solely from the energy produced by the solar panels indoors in ambient light. It doesn't even need direct sunshine, so it's really power efficient. And in the IoT age that we're entering, that's very important. Things like sensors get installed in very hard to reach places, embedded in walls and under the floor. You can't be changing the batteries every month, so power efficiency is really important. Bluetooth Low Energy also lets you form these point-to-point connections between 2 devices. If you've got something like a Fitbit, an activity tracker, that's using Bluetooth Low Energy. Your phone almost certainly has both of these Bluetooth flavors on it, and you probably don't even know this because you don't need to know, it just works. That's one of the nice things about it. So Bluetooth Low Energy can also form point-to-point connections, but it also has the ability to broadcast data. So that's a kind of one-to-many as opposed to one-to-one communications topology. Who knows what a Bluetooth beacon is? Ooh, 1, 2, possibly. It's like an auction. Did he just bid? I'm not really sure. Possibly 2 people, possibly 3. Not entirely sure who that one's going home with. So Bluetooth beacons are like tiny Bluetooth transmitters that just broadcast a unique ID. And you're walking along with a smartphone with an application on it. It's receiving that broadcast and mapping the ID onto some form of information, usually a location. If I'm in range of the beacon that's installed over there, then I must be in this room. So they're used at art galleries, airports, shopping malls, those kinds of things. Bluetooth Mesh, subject of today's talk, is relatively new. The specification was released last year in the summer. Now we're seeing products that use it being implemented. And in terms of those topologies, this is about many-to-many communication. Lets us form networks of tens of thousands of devices. And it was largely designed in the first instance for smart buildings. It's not just for that, but in terms of the use cases that were driving the technical design, truly smart buildings was really center stage with wireless lighting systems and things like that. So here's the relationship between them. So BR, EDR, and Bluetooth Low Energy, they're both radio technologies, radio communications stacks. And Bluetooth Mesh is not, it's a networking stack, and it sits on top of Bluetooth Low Energy. So all the actual comms that goes on in a Bluetooth Mesh network is using the Bluetooth Low Energy radio, okay, which is very low latency, very power efficient, very fast. I'll talk about scalability later on. It's much faster than similar mesh networking technologies, and that matters when we come to scalability. But that's how they relate to each other. So I want to kind of introduce you to Bluetooth Mesh now. I'll start with some network level concepts, and we'll sort of drill down and explore the technology and find out more about it. So let's start at the top. So 3 keywords, they all conveniently start with multi. I didn't make this up, they just happen to, okay? Coincidences do happen. The first is multi-hop, okay? So what we're used to, what we're accustomed to with wireless communication is that devices can only communicate if they're in direct radio range. If the 2 devices move too far apart, we go out of range, the connection drops or something, and they can't talk anymore. Mesh networks in general don't work like that. Data is exchanged through a messaging paradigm, and messages get delivered to their destination either directly, if the destination device is in direct range, or indirectly by hopping across the network from device to device to device through a process called relaying. I'll tell you more about relaying in a few slides' time. What this means, though, is you can have a mesh network that encompasses a very large area. Now, the point-to-point range of the Bluetooth Low Energy radio is way longer than any of you realize, I'm going to guess. Let's waste some time. Somebody tell me what the range of Bluetooth Low Energy is, despite the fact I've just given you a big clue. Someone say 1,000 miles. It's not that. Any idea? What's your experience of Bluetooth and range? 10, 20 meters. Thank you. Not uncommon to discover that with actual products. The range that Bluetooth Low Energy has at the version which Bluetooth Mesh uses, which is actually Bluetooth 4, as opposed to the latest, which is Bluetooth 5, it's hundreds of meters. And I know this not because somebody told me, but because I tested it myself, because I don't believe anything anyone ever tells me, right? So I've been out in a local park with a collection of smartphones and a microcontroller, and what I actually found was quite strange. I found that the cheapest smartphones had the best range, and the most expensive smartphones that didn't belong to me because they're too expensive, I'm not going to name names, had the shortest range. So the shortest range I encountered was 30 meters, and that was a very expensive state-of-the-art smartphone. The cheapest smartphone, which was on my kids, so Motorola Moto G, had a range of 300 meters. Okay? Same technology, same device transmitting to them. So range is not just about transmission power and things like this, it's about both receiver and transmitter. And the range I'll talk about is the potential range that the technology has. What you experience in an actual product may vary considerably as a consequence of design decisions that product designers make. Presumably, the guys and girls who designed the expensive smartphone thought, 30 meters, that's fine. That's fit for purpose. Let's move on to the next job now. And they're already cramming lots of things in their smartphone case, so they moved on. So your experience of the technology might not be doing it justice. It's certainly hundreds of meters. In a building, it'll be less with barriers. Now, in terms of multi-hop, we can do up to 127 hops, and messages travel at the speed of sound. So 127 times, however many tens of meters we're going to get inside a building, it's a long way. So we can cover a whole office block, possibly a collection of offices in a business campus, maybe a whole neighborhood with Bluetooth Mesh. Multipath, to move on to the next of my multis, is all about reliability. So I was actually in attendance when our mesh working groups, like a project team, got together to discuss Bluetooth Mesh for the first time. And the discussion really was all about requirements, not about technical solutions. Top of the list, were two categories of requirement. One was security and the other one was reliability. And producing a wireless networking technology like this that's sufficiently reliable in places like large buildings is very difficult. Some really tough engineering problems there, all sorts of issues. Bluetooth Mesh consequently has a variety of strategies built into it that are all about maximizing reliability, and one of them is this multipath idea. When one device sends a message, without you needing to do a great deal, not quite by magic, but almost, copies of that message will travel through your network via multiple paths to arrive at the destination. The first copy to arrive will be acted upon, other copies are discarded, but of course if one of those paths fails, because one of the relaying multi-hop devices is broken or there's a physical barrier that wasn't there before blocking radio communication, it doesn't matter. So this is basically redundancy. It's architectural redundancy in a networking system. And you don't really have to do a great deal. A little bit of thinking in your network design is required, but not much else. So the third of my multis is multicast. And multicast is more important than it might sound. The entire system is built around the idea of one device talking to multiple other devices. That's the basic premise, that will be the general case. I flick a light switch, all the lights in the conference hall come on. I have a sensor communicating something, maybe an occupancy event, somebody walks into the room, the sensor reports that someone's in the room, but it's telling lots of different devices. It's telling all the lights, it's telling the blinds that can come down or go up, it's telling the air conditioning system. So most of the use cases are what we call multicast scenarios. And it's designed around this in a number of ways, but one of them really lends itself to being very scalable, and I'll tell you more about that in however many slides' time. So those are some high-level kind of network-related concepts. Now in a network, a device that's part of that network, we call it a node. That's the term that we give to it. And nodes can take on special roles in your network. They can provide special network services. Doesn't matter what type of product it is, whether it's a light or a switch or an air conditioning unit or a thermostat or whatever, it's all software. So there are configuration flags you can choose to set when configuring your devices when you first install them that instruct the device to play a special part in the network. And one of them I've already mentioned, that's relaying. So you can say to, maybe I could say to that light there, be a light, responds to all the messages relating to lighting that I might send you because you're a light, but also be a relay, and relays will retransmit any messages that they receive. For small networks, you don't need any relays if everything's in range. For slightly larger networks, you'll need a few relays and probably don't need to think about it too much. You probably have one upstairs or something for a smart home. For larger networks, you have to think about it. If you have too many relays, you will waste all of your radio resource. You'll be retransmitting everything that comes in, you'll be consuming lots of radio spectrum, and you will impact your scalability. So the sort of rule of thumb guideline we give is that 5% of the nodes in a larger network will be relays, but probably no more than that. However, the way you'll approach this is through some design work before you create your network, and then some testing and optimization on site to check how things are working. But that's the relay, and the relay is the basis for multi-hop and for multipath. If I've got two relays here, I send one message, it will go via both relays, and that's how it travels across the network via different paths by going through different relays. So this one I like because it's got a nice name. This is about friendship. Oh, isn't that nice? It's actually a technical term. Isn't that lovely? They could have called it something obscure, maybe an acronym for us to learn, but no, this is friendship. So, one of the ways you can look at the different types of devices that you might choose to have in a mesh network is in terms of their power requirements. Power is really important in all these things. We have power-rich devices that are connected to the grid all the time, lights, for example. We have power-poor devices that are not, things like sensors embedded in the wall, which have to be battery-powered or maybe some other approach. Very much a two kind of class society here. Bluetooth Mesh allows us to tell devices, if we want to, which of those two families they fall within. We have power-rich devices we can call friends, and we have those which are power poor, we can call low power nodes. So it's a configuration flag we can switch on. The purpose of this approach is as follows. Power consumption from a wireless communication point of view is directly concerned with use of the radio. If the radio is asleep doing nothing, we have no problem. If it's transmitting or waiting to receive, it's using power. If it's waiting to receive and doesn't receive anything, doesn't matter. It was using power all the time it was waiting. So if you imagine I have a temperature sensor, its job is to transmit temperature readings only if they go above a certain level or below a certain level. Maybe that sensor only transmits readings 2 or 3 times a year on really hot days or really cold days. So at that stage in the description, I do not have a power consumption problem because this thing hardly does anything. It hardly ever uses the radio. But I have a problem because it also needs to be able to receive configuration messages to change those thresholds, to tell it we're in the midst of a key rotation change, one of the security things in Bluetooth Mesh. So it has to have the radio on in receive mode pretty much all the time, otherwise it will miss messages. So now I've got a terrible problem. I'm going to have the radio on all the time on this really low-powered device, but most of the time it won't receive anything. It's really wasteful. What do? So that's where friendship comes in. So the Bluetooth Mesh specification defines a number of communications protocols, and one of them allows low-power nodes to discover devices that have been designated friends, that are power-rich. And this happens dynamically when you first set up your network. Kind of scan around and go, oh, you seem to be a friend, I'm a low-power node. Shall we be friends? And they form a relationship, which I kid you not, is called friendship in the spec, after which the friend helps the low-power node. And it works like this if you watch the graphics here. So any messages addressed to my sensor actually get delivered to the friend, because it's listening all the time, it's not got a power consumption problem, it can afford to do that. My sensor, meanwhile, is asleep. Excuse me. And it has its radio switched off, and it can do that because it's fine, my friend will look after any messages that get sent to me, and it will store them, and I can have a nice sleep. It can stay asleep for days if it wants to. We decide how often it's going to wake up. When it does wake up, it switches the radio on, it sends a message to its friend, says, do you have anything for me? Switches into receive mode, receives anything that comes back. And that all happens in milliseconds. So we've really, conserved enormous amounts of power, but the sensor's been reconfigured, and life is good, okay? It's the power of friendship. Last special role is called the proxy. Now, 10 million devices every day, and I might have mentioned that at the start because I kind of like that fact. There are a lot of Bluetooth devices out there already. And not surprisingly, we wanted to make sure that at least some of those existing devices, in particular things like this, and laptops and the like, would have some way of becoming part of a Bluetooth mesh network. Now, most of the use cases involving mesh networking and the devices that the mesh network contains are kind of small, microcontroller-based devices, switches and sensors and stuff like this. But there are times when you want to have a control panel to monitor and control your entire network or parts of it, something with a user interface. And of course, smartphones, tablets, laptops are great at that kind of thing, but they don't have a Bluetooth mesh stack on them. So proxy nodes understand both the APIs or the messages associated with the basic Bluetooth low energy. It's something called GATT. Who's heard of GATT? Anyone? It's a thing, I'm not just making a noise here. GATT. It's a word. It's not a word, it's an acronym, G-A-T-T. So that's kind of the protocol, if you like, that sits on top of Bluetooth Low Energy on your phone. And you've got APIs for Android, iOS, web Bluetooth as well, that let you work with GATT, but not Bluetooth Mesh. But proxy nodes luckily understand both those worlds and consequently can sit in between the two and do some translation. So if we designate one or more of our devices in our network to be a proxy node, then I can have Bluetooth applications on phones, tablets, on desktop computers that can actually engage with interactions with the mesh network. There you go. So how do they talk to each other? Well, I've kind of hinted at this already. It's all based on messages. And the specification defines don't know, hundreds of message types, lots of messages defined in the spec. It's worth mentioning this spec here briefly. The reason we have a Bluetooth mesh official standard technology and the reason there is a specification is all about interoperability. I've been speaking at smart building conferences for many years, and I can tell you they are not accustomed to being able to buy stuff to populate their building with from any manufacturer that they choose, because there aren't the standards governing interoperability between different types of devices. So with Bluetooth mesh, everything is defined from the way the radio works, and this is analog stuff, it's not even digital, it's about waveforms and frequencies and all that stuff, that's right at the very bottom, all the way up to the very top where we define how key behaviors of products should function. So everything's defined, therefore you get interoperability between different devices. And message types, that's all part of that definition aimed at giving interoperability. So messages are things that we send to communicate and interact with other devices in the network. Devices contain what we call state, really collections of data items that describe and control different aspects of a given device type. One I've got showing up there is the generic on-off state. Guess what that indicates? It indicates whether the thing is on or off, and it's generally applicable to any type of product, hence generic. I can send messages like generic on-off set, and that will change that state value from on to off, or from off to on. So that's the kind of sense of what's going on with messaging. There may be, however, many types of distinct message defined in the spec, but they fall under 4 possible headings. We have set messages, of which there are 2 variants, I'll explain in a moment. If I send a set message, that will change the value of some target state in one or more devices. We have get messages. If I send a get message of a given type, some state value will come back to me in a status message, which is the 3rd message type there. And in fact, devices can announce their state values by sending status messages whenever they choose to anyway. The 2 variations of the set message, I've got acknowledge messages. If I send a set message, so generic on-off set, brackets 1 will turn something on, I'll get a status message back to confirm that it happened. Unacknowledged messages, not surprisingly, don't generate a response. Now, what may surprise you is that it's the unacknowledged messages that we use all the time. Acknowledged messages are a real nightmare in mesh networks. For an example, there's an internet RFC called something like, I think it's IP Group Multicast. I think that's the name of it. And it describes, because I think they found that they have no choice but to describe, all the problems associated with protocols that are of the sort request-response. Almost all protocols you've ever worked with probably are request-response type protocols. In multicast systems, they don't work very well because they don't scale. A number of things happen. Consider this. First of all, if I send a multicast message to 100 devices, I need to know the identities of all 100 devices so I can check whether or not I got a response from each of them. If I don't get a response from some of them, I need to resend again. And very quickly, you generate a storm of messages going backwards and forwards, and I didn't receive one from them. You consume all the radio resource, which is finite. This is what limits your scalability. And things get very complex in your code very, very quickly. So unacknowledged messages sent in special ways to maximize reliability is a much better strategy, and it's how Bluetooth mesh works. Bit more on messaging. So who's heard the phrase publish and subscribe? Yeah, we didn't invent this, so it's a publish and subscribe messaging system. And the way it works, if we take lights again as a good example, if I install some switches, when I install them, I'm going to do a couple of things. I'll make them part of my network doing something called provisioning. That's a security process. Equips them with some special security keys, and I'll then configure them. One of the things I'm going to configure is I'm going to tell the switches what address to publish, send messages to. And we have an addressing scheme which includes group addresses, which are the ones you use almost all the time. Devices do have unique addresses, but you almost never use them. You use them when you're configuring the device because that's a one-on-one conversation. After that, it's all about group addresses, even if the group only contains one member. So I'm going to configure my switches in the hallway of my house to publish to a group address that really means hallway lights. Each of the lights I'm going to configure to subscribe to that same address. Now, the switches know nothing about the lights that they're controlling. They don't know their addresses. The lights know nothing about the switches that are controlling them. They just know that if there's a message addressed to this address that they should respond. Okay? So the two are decoupled. And the major advantage here is that if I make changes, like I change one of the lights, put a new one in, I don't have to reconfigure any of the switches. Might not sound like a big deal in the context of your own home, but hotels can have tens of thousands of lights. It becomes a big deal quite quickly if you're forever having to reconfigure your network just because there was a small change. There are other mesh networking technologies where you have to run reconfiguration, rerouting table building things overnight. Nightmare, okay? It doesn't scale from an operational point of view. Now, I've talked about nodes. That's the name we give to a device that's a member of a network. They actually have a structure, and if you're writing firmware for these devices, you'll see this, and you'll probably get involved in describing it in code. So a node is a physical thing, let's say, and each node comprises one or more things we call elements. And elements are individually addressable, so they are the things. It's a logical construct, might correspond to something physical in the product. These are the things that have the unique Unicast addresses. I'll show you an example on another slide in a moment. Sitting inside elements, there's something I haven't mentioned yet, and these are models. Now, models are essentially standard, as in compliant with something we put in the spec, standard software components that perform one type of task. And what a product does is a consequence of the combination of standard models it's been equipped with. So, you'll see in a moment, if I want my lights to be able to respond to on-off messages, I'm going to make sure that the elements in my lights have the generic on-off server model. Okay? And there are all sorts of other models concerned with all sorts of things in the spec that I might choose from as a kind of product designer. I've mentioned state already. I just said, well, these things, they have state, and we change those or query those things by sending messages. In fact, states belong to specific models. It's the model specification that tells you what states are inside that model. So it's an almost hierarchical kind of relationship between node containing elements, which contain models, which contain states. So there's some examples. We actually have clients and servers. So clients models simply produce or consume messages. They don't contain any state. Server models do contain state. So the simplest one of all from the spec is the generic on-off client and the generic on-off server models. So if I want to switch stuff on or off, those are the models I'm going to have. And I can change levels, I can change the hue of lights, I can change color temperature, I can support any type of sensor you care to imagine from using the appropriate sensor models and so on. So there's lots of different types of things there. I'm using the simplest for examples here. So there's a product that is one physical thing. It'll be one node in my network, but it'll have 3 elements inside it because each of those LEDs will be individually addressable. Okay, and I'm going to control them independently from each other. And you can see that I've given some examples of the models I might have. So again, generic on-off server in there, because of course I want to switch my lights on or off, but I've also got the lightness server. Lightness is the term that the lighting industry uses for what I would call brightness. Lighting is way more complicated than you can ever possibly imagine. I had no idea. Is anyone here from the lighting industry? No, okay, I spent like 2 days listening to people talk about lights once, and I'm like, what are you talking about? Yeah, it's a lot more to it than you realize, especially commercial lighting, some really complex stuff. But we've got models designed specifically for those kinds of products. So, you should have a reasonable, I hope, mental image now of what this mesh stuff is about. Very brief introduction to security, big subject, but let's just give you some key points here. So, one of the things I said was that there's a process called provisioning. Now, when you take a product out of its box, at that point in time, it's not a member of your network. Okay? It's just a device. we have to equip it with a number of security keys, and it's possession of those keys that makes it part of your network. I'll say a bit more about this in a moment. So again, the process is called provisioning. You're going to use a smartphone application from one of the manufacturers, and it will equip your new device with the appropriate security keys. Now it's part of your network. Who's heard of pairing? It's like saying, who's got a smartphone? I already know the answer. So in the world of other Bluetooth technologies, pairing is about establishing a trusted relationship between two devices. And once again, there's a handshake and they end up equipped with some keys that they can use to secure communication between them. So this is analogous to pairing, but it's not the same as pairing, because if you had to pair each possible permutation of your devices in your large network, I can have 32,767 devices in my network. If I had to pair each one with each other one, you can do the maths when you get home. It would be a really, really, really big number, and I would never finish that task. So clearly we needed a different way of equipping devices with keys. It's called provisioning. It leverages some of the same kind of cryptography, so elliptic curve digital. The Diffie-Hellman stuff is used to protect the handshake and so on, so there's some similarities, but it's a one-on-one thing that we do to equip devices with keys. Yeah, elliptic curve, Diffie-Hellman, yeah, lost it there. So, who's worked with Bluetooth, low energy in particularly, as a developer? And you've done any coding with Bluetooth at all? 1 and a bit people, judging by the height of the hand there. Okay, so with the other Bluetooth technologies, you're basically working with a security toolkit, and everything is optional. There are things that you can include or choose to exclude from your application and product. It's entirely up to you. And the thinking is very simple. It's that we, the Bluetooth Special Interest Group, we know nothing about your product. We know nothing about the sector it's being used in, nothing about the types of people using it, or the value of the data. So we give manufacturers all these capabilities. They have to do their risk assessment. They have to decide which security capabilities that their product must have. It's entirely up to them. And they might decide that no security is absolutely appropriate, and there are plenty of devices like that out in the world. Bluetooth Mesh is not like that at all, because a network will comprise products from all sorts of different manufacturers. We can't let low security or absent security in one device affect the security of the network as a whole. That would not be allowed. So it's an entirely new approach to security in Bluetooth. It's all mandatory. Every message that gets sent is encrypted and authenticated. So if you know your crypto, this is using AES-CCM. So every message is encrypted, but can also be authenticated, meaning that it's not possible to kind of fake messages and inject them into the network, because without the right keys, they'll fail the authentication checks. We could do some cool things. We do something cool to do with application layer and network layer separation. So every packet that gets sent has some fields in it that are to do with the networking layers of the stack. You can imagine the way a stack normally looks. Right at the top, we've got stuff that's to do with kind of application layer behaviors, things to do with models, switching things on and off, turning things up and down. That's the application layer. We use 2 separate keys for securing the network layer versus the application layer. And one of the reasons for doing that is it means that network services like relaying, which I mentioned, can be undertaken by absolutely any device because they will have the network key. But if they don't have the appropriate application key, they can't decrypt the upper layers. So applications in the world of Bluetooth Mesh are whatever you decide they are, but typically it'll be things like lighting, that's one application, air conditioning, that's another application, and you decide as you're setting your network up, and you create new application keys for each distinct application area. So if I'm sending a message from a sensor that's part of the air conditioning application, it will have its networking fields encrypted with the network key, its air conditioning related fields encrypted with the air conditioning application key. But my lights can relay these messages because they can decrypt the networking fields, that's fine, but they have no clue what's going on in the upper layers because they don't have the right keys. You know, maybe these are messages from the security gates at the front of house. Absolutely don't want other devices to be able to decrypt this stuff. So we're separating application and network layer there. We can also do what we call area isolation. So yes, there's a network. Yes, there's a network key that defines membership of that network, but you can also create subnets. And subnets are not like they are in the world of IP. A subnet really just has a distinct network key. And subnets can be any physical shape you like. They can be inside each other. They can be long and thin. Absolutely no restrictions there. So you could have one subnet which is a corridor, all the lights in one corridor, for example. But think about hotel rooms, okay? One of the things you absolutely want to make sure happens is that the occupant of one room can't control the devices in another room. So the idea is that you walk into the hotel, instead of issuing you with a card, they actually provision your smartphone, and it's given the appropriate keys for the subnet that is your hotel room. So you go in and you've got all these cool smart devices you can control from your phone, very thrilling, but you can't control your neighbour's stuff because cryptographically you've drawn a boundary around those physical areas by creating different subnets which have correspondingly separate keys. Messages are all obfuscated as well, so security, interesting topic, lots of cunning and devious people out there. One of the attacks is called, one of the types of attack is network pattern analysis. So rather than trying to attack one message, you're looking for patterns over a period of time. And from that, you can deduce things like habitual movement of devices and the people associated with them, potential privacy issue there. So we also obfuscate all the network headers as well, that makes that very difficult. What else we got? So some really common attack types. Who's heard of a replay attack? Ooh, we've got some security people. Okay, good. So replay attack is how cars are still stolen, despite it being an attack that was, I think, recognized decades ago. So you kind of hide behind a pillar in the car park. Person walks up, presses the button to send a message to their car to unlock it. You record that message. Next day, you just replay it and the car opens when they've gone to the office or to the bank or something, you steal their car. So that's a replay attack. Can't do that with Bluetooth mesh through a sequence of a series of very large sequence numbers that are unique for every message. Trash can attacks, that's to do with taking devices that have been discarded out of the trash and extracting those keys and then using those. We have a mechanism for responding to that involving key rotation. What else we got? And provisioning, that's the thing I mentioned at the start. That's where it all starts. You provision your devices, that provides the raw material, the keys that feed all of these cryptographic processes that make Bluetooth mesh pretty secure. So there you go. There's some pictures of keys. If you could look at them, please. All clear? Good, excellent. So, so those are the three types of thing. I've kind of mentioned two of them anyway. So the network key, plus any associated subnets, that really defines membership of a network and is used for securing network layers, the network layer of the PDUs from the stack. Application keys I've already mentioned. They're mathematically related to the network key, so you can't take an application key from some other network and use it on yours. Again, that's another security constraint. And each device does have a unique device key. Now, the only time we go kind of one-on-one talking to one device is when we first configure it. Then we use its Unicast address to talk directly to it, and we encrypt that communication using that device's unique device key. That's the only time that stuff's used. So let me show you how some of this is used together. Ooh, 10 minutes to go, and I've got loads more left. Loads. I might either go really fast or just skip some stuff. So, really briefly, imagine I had some switches, some lights, and some sensors. Here's what you're likely to see inside them in terms of those models. I want to be able to switch my lights on and off, so I'm going to have the generic on-off server model in the lights, and the generic on-off client model in the light switch, so it can send generic on-off set, brackets 1 or bracket 0 to switch things on and off. Lights being lights, though, I'm going to have some other stuff in there. They're dimmable, so I've got the lightness server, and these are also colored lights, so I've got the light HSL server, that's hue, saturation, and lightness. You'd be familiar with that color model from programming, I imagine, so I can change the color of my lights wirelessly as well. Let's bring the sensor into play. I've got, what should we do today? Okay, I've got some ambient light sensors in the room. This kind of works for all sorts of different sensors. And ambient light sensors are measuring the ambient light level throughout the day. Also, my lights have got the LC server model, that's lighting control. And the way these things can work together leverages something I haven't mentioned yet called state bindings. The spec defines relationships between states in the same model or in different models. What it means is that if one state value changes, all the other states that are bound to it get recalculated. So we get relationships between states. In my use case here, let's say a cloud moves away and the sun beams into the room and it gets nice and bright. The sensor, reading those ambient light levels, is communicating, it's publishing sensor messages to devices on some group address. In this case, it's the lights in our room. The Light LC server is receiving those messages and the state data that they contain, but it has a binding with the light lightness server, and so as a consequence of the ambient light level in the room being brighter, it's telling the light lightness server to turn the artificial light down. So we're saving power, we're saving money, and it's good for the environment. Conversely, of course, as we get later in the day, it starts to get dimmer, or maybe the weather's very, very bad, the light level being reported is lower. So this is very subtle. This is a very granular thing. It's very subtle and very gradual. The lights get a little bit brighter to compensate for the fact that there's less ambient light in the room because it's darker outside. So we keep a nice constant light level throughout the day. This is called daylight harvesting in the world of smart buildings. And there are lots of other sensor-based use cases like that. Scalability. 8 minutes to do this in, probably not possible. So what I'll do is I'll just rush, okay? So all I want you to take away here actually is this. Not all wireless technologies are the same. Stating the obvious, I know, but honestly, I've met lots of people who don't quite appreciate that to be the case. So if your job was to select the wireless communications technology upon which to base your product line, you've got some thinking to do and some evaluation, because it's a kind of bet the business type decision. Choose the wrong technology, something that proves not to be as scalable as you thought it might be, and you're finished. It sounds dramatic, but it's a fact. Your products will fail, your business will probably fail with it. So it's a really key decision for companies that are looking at this kind of stuff. The number one constraining factor in the scalability of a mesh networking system like this, and there are others. Who's worked with other mesh networking technologies? There are two that begin with Z. I can't say their names. I burst into flames if I say them. Yeah, so there are others. Bluetooth is quite late to the market with this. And they are absolutely not all the same. So the number one constraining thing, write this down, it's very important, it's how efficiently and how you use the radio spectrum. Radio is a shared medium. If you choose a frequency, only one device can use it at a time. It's a fact. It's no different. Ethernet's essentially the same, okay? We can all use the medium or the media one at a time. We have to take turns, or we have to respond to two people trying to use it at the same time. That's called a collision in some ways. It's a very common issue. It's not just about wireless communication, rather. It's about communication in general. But if two devices transmit on the same frequency during a time period where this communication overlaps, the two packets get corrupted. It's called a collision, and we've lost them. The way I like to think about it is this. Think about light instead of radio, because we can see light and we're quite familiar with it. Imagine I had a red light over there and a blue light in the corner. Red light coming on means one thing, means one. The other light coming on means two or something. It has some meaning. Red light comes on, I know what that means. Blue light comes on, I know what that means. If one comes on and the other one comes on at pretty much the same time, I get a different colour. I don't really know what that means. It's not defined. They've corrupted each other. It's exactly the same with radio communications. So the point at which we start to get lots of collisions is the point at which things start to not work properly, and that's when we start to say, okay, it's not scaling anymore. We've kind of reached a limit, because the lights don't come on when they should do, because there are all these collisions taking place. What are the factors that will lessen the probability of collisions in a busy network? The answer is very simple. If you're transmitting a large packet of data to get a specific type of task done. So I have to send that much data to tell all the lights to turn on in this room. It'll take a certain amount of time occupying that frequency. It's a serial transmission. So chuk, 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 long packets. I'm hanging onto the radio for ages, okay? And during that time, anyone else transmits, we get a collision, we've lost it. And because it's a long packet, the probability of that collision happening is relatively high. Short packet is in the air for a fraction of the time, and therefore the probability of a collision is so much smaller. Therefore, we can get more work done before we get to that level where we start to see lots of collisions. So Bluetooth Mesh has tiny packets. They're 29 octets plus a bit of header stuff for the Bluetooth Low Energy radio. It's about a third of the size of comparable systems. This is because it was designed specifically for this job and to be as scalable as possible. So big packets, bad. Small packets, very good. The second issue is how fast is the radio? When we're transmitting bits using a radio, really we're transmitting what we call symbols. They're the analog equivalent of bits. And there is a symbol rate associated with radios. Bluetooth is 4 times faster than any of the other low-power mesh communication systems. It's a megabit per second, a megasymbol per second, to be technically correct. Other comparable ones are limited to 250K bits per second, and they're limited because they use lower layers of a protocol stack that they don't even own. It's IEEE 802.15.4. So those other mesh, at least 2 of those other mesh networking technologies sit on top of 802.15.4. They don't own it, so they can't change it. They will never go faster than 250K bits per second. And this thing about speed is not about video streaming. It's not about raw power bandwidth. It's about getting a specific amount of data over the air as quickly as possible. So we're holding that frequency for as short a time as possible, so the probability of collisions is as low as possible. And that's how you get to scale to very large numbers. Okay, the devil is in the detail. It really is. They're not all the same. And I've kind of just told you, I think, everything that's in the next few slides. Look, I could have shown you these pictures, and it would have made a lot more sense. See, look how much capacity we've got. We've got tiny, tiny little vehicles carrying the same amount of stuff, and we actually use 3 frequencies anyway, not just the one that all the others use. So there you go. Right, I'm going to show you a video demo. I sometimes do this live, but I didn't really have time today because I sort of flew in, got here. So here's a thing, with time, only a few minutes, this bad news, that I made at home on my kitchen table. Now, normally, let me just pause this. So normally, devices are microcontroller based. They're small devices sending and receiving messages in the way we've described. I created something that let me make a proxy client using web Bluetooth. So what we've got here are 64 nodes. They're BBC microbits if you're interested, but each one is an independent microcontroller with a mesh stack on it using an OS called Zephyr. And I've programmed them so they've got the generic on-off server model and the generic level server model, so I can change levels in various different ways. Sitting next to my laptop, at the bottom there is another device. Oh, go away. Get out of the way. Is another device which has more memory. It's acting as a proxy. There, look, it says so just there. And then I've got my laptop, which is able to use kind of normal Bluetooth Low Energy, not mesh, to talk to the proxy. And my UI lets me scan and connect to the proxy. That's what I'm doing now. And then I am going to speed this up in a moment, but using the UI, that kind of looks like the 4 Lego panels that I've nailed those microcontrollers to. Top right-hand corner there, DST is one of the field names in the messages. That's destination address. I've got 3. Each device has subscribed to 3 group addresses, one for the panel that it's a member of, one for the row that it's in, and one for the column that it's in. There was a special address up there a second ago, FFFF. That means all nodes in the network. You're not meant to use it, but I thought, hey, it's just a demo, so I'll use it. I've just sent generic sets on to FFFF. They all come on. Fantastic. This is like my first test. It's like a miracle. It works. Now I'm going to send a message to switch off. So I'm sending generic sets on, off, unacknowledged. That's the full name. But this time with a 0 to switch the thing off. And then I'm changing the group address, so now I'm just addressing one panel, so that could be like a room in a house or something, to see how this stuff works. Whizzing forwards a little bit, don't need to see all this, so I'm just exercising the different group addresses here. Using Unicast addresses there. So generic level server, I haven't mentioned before, is a bit more sophisticated than you might realize. I can send absolute level values to say to devices, switch to this level. And here I've got 25 LEDs on each of these microcontrollers. I'm using the number of LEDs to indicate the level. And with my UI there, I'm just setting things to arbitrary levels. So those are absolute levels, that's generic level set, that's the message type. I've also, so there you go, I've just switched them all onto full level there. What am I doing here? So I've also got generic delta set, where I can increment or decrement the level by a specified amount. So I've selected a small delta, and I'm now incrementing one LED at a time. And I can obviously go in the other direction as well. Actually, I'm increasing the delta here, so I get increment by a bigger delta. There we go. What else have we got? Do we want to see all this? I kind of think we do. Let's move on. Yeah, and last one's move. So move is a dynamic transition of the level. So what we do is you say we want you to change by a certain amount in a certain time. So a certain amount in a certain time, that's speed. There we go. So I'm transitioning to a new level in a certain time, and you're allowed to repeat this. It's up to you whether you wrap round or stop at the top. Spec allows either to be done. So it's a really simple mesh demonstration there, and I'm over time. Brilliant. If you want to know more, 2 slides now. We have loads of stuff on our website. So our website is bluetooth.com. Remember that? You've got a sticker, okay? Every time you look at the sticker, you will find your way to all sorts of reading material. I'll recommend one. It's called the Bluetooth Mesh Technology Overview. It looks like it might be 25, 30 pages long. It isn't. It's 8 pages, but marketing put lots of graphics in it to make it look pretty. It's 8 pages. It's nothing. You'll read it in half an hour. You'll get a really good understanding of what we've talked about today and more. If you want to go hands-on, we have lots of hands-on stuff as well. Bluetooth Mesh Developer Study Guide is like a small book, actually, but it's got about 5 hands-on development projects where you can make pretty much the stuff that I showed you in the video, bar the Proxy client, which is covered in the Mesh Proxy Kit. So there you go. I'm at the end. Thank you very much for listening.
Thank you very much.
Thank you very much.